Europa, the ocean we can't touch. An ocean larger than Earth's, sealed under ice. That is not exaggeration. Beneath the frozen surface of Europa, one of the major moons of Jupiter, lies a global ocean believed to contain more liquid water than all of Earth's oceans combined. But we cannot see it. We cannot sail it. We cannot drill down to it. Kilometers of ice stand between us and whatever lies below. Europa appears at first glance simple, a smooth pale sphere streaked with dark reddish lines. Few impact craters, no towering mountains, no thick atmosphere. But the surface is deceptive. Europa is one of the most geologically intriguing worlds in the solar system. The normal, how tidal heating works. Europa orbits deep within Jupiter's gravitational field. It does not travel in a perfect circle. Its orbit is slightly elliptical, and it is locked in orbital resonance with two other moons, Io and Ganymede. That gravitational interplay constantly flexes Europa's interior. As Europa moves closer to Jupiter, the planet's gravity stretches it. As it moves farther away, the stress relaxes. This continuous flexing generates internal friction. Friction generates heat. This is called tidal heating. Even though Europa is far from the sun, tidal heating may be sufficient to keep water liquid beneath its icy shell. The ice crust is estimated to be several kilometers thick, possibly tens of kilometers in some regions. Beneath it, evidence suggests a salty global ocean in contact with a rocky mantle. Not a pocket, not a melt zone, a planet-wide ocean. Clue 1. Cracked ice. Europa's surface is crisscrossed with long, dark fractures called lineae. These cracks stretch for thousands of kilometers. Some appear to have opened and refrozen repeatedly. Others intersect in complex networks, suggesting shifting plates of ice. In certain regions, known as chaotic terrain, the surface looks broken apart and reassembled. Blocks of ice rotated and frozen back into place. These patterns imply motion. Ice that fractures. Ice that shifts. Ice that may float on something softer beneath. The lack of heavy cratering suggests the surface is relatively young, meaning it is being resurfaced over geological time. Something below is active enough to reshape the ice above. Clue 2. Induced magnetic hints. In the late 1990s, the Galileo spacecraft flew past Europa multiple times. Its magnetometer detected something unexpected. As Europa passed through Jupiter's powerful magnetic field, measurements suggested the presence of an induced magnetic field, one that varied in a way consistent with a conductive layer beneath the surface. Salt water is conductive. A global ocean of salty liquid, water could generate exactly such a magnetic signature when interacting with Jupiter's field. This was not direct detection, it was inference. But the data strongly supported the presence of a subsurface ocean. Clue 3. Surface exchange. There is also evidence that material from below may reach the surface, and that surface material may cycle downward. Spectroscopic observations suggest salts and possibly other compounds have been transported upward. Some models propose that briny water may occasionally rise through fractures, freeze, and deposit materials onto the surface. There have even been tentative detections of possible water vapor plumes, though these observations remain under study and require further confirmation. If exchange occurs between the ocean and the surface, it changes everything. It means the ocean is not completely isolated. It means chemistry could circulate. It means that the surface may hold clues to the ocean's composition. Europa's ocean is dark. Sunlight cannot penetrate kilometers of ice. Energy would need to come from elsewhere, likely from tidal heating and possibly hydrothermal interactions at the ocean floor, where water may contact rock. On Earth, hydrothermal vents host complex ecosystems independent of sunlight. But analogies must be used carefully. Europa is not Earth. Its ocean chemistry, pressure, temperature, and energy gradients may be radically different. The conditions could be favorable for complex chemistry. Or not. We do not know. That is the tension. Europa offers strong, converging lines of evidence for a global ocean. Surface geology suggesting mobility. Magnetic data implying a conductive layer. Models showing tidal heating sufficient to maintain liquid water. but access is blocked. Unlike Enceladus, Europa does not continuously vent its ocean into space in a way we can easily sample. To reach its ocean directly would require drilling through kilometers of ice in an extreme radiation environment dominated by Jupiter's magnetic field. It is one of the most technically demanding exploration targets in the solar system, and yet it remains one of the most compelling, because if there is liquid water, energy, and chemical gradients, the question inevitably follows. Not whether it must host life, but whether it could. And if something is alive down there, microbial, chemical, unfamiliar, would we even recognize the signs? Life elsewhere may not resemble terrestrial biology. It may not use the same molecular structures. It may not produce familiar biosignatures. It may not even fit our definitions cleanly. Europa's ocean is hidden, sealed, pressurized, untouched by sunlight. We have images of its surface. We have magnetic measurements. We have models. But we have never touched the water. An ocean larger than Earth's, trapped beneath ice. If something moves in that darkness, we would not see it. Not yet. And the deeper question may not be whether life exists there, but whether we are prepared to recognize it if it does.